f0, it could be that, so it's bounded below by that. But bounded above, it's going to be less than or equal to, or not equal to, I should erase that. Less than n times our modulus m. The reason for that is because all of these could be m minus 1. This could be m minus 1. It's not, but m minus 1, so on and so forth. And so we'd have f0 in this case. If all of those were m minus 1, then f0 would equal n times lowercase m minus 1, which is obviously less than n times m. So we get to the next row, f1 here, and again that's going to be the same thing. It's just now we're going to the next row and the next column and so on. So all of these sequences, we can say that for every element of the inverse of the number theoretic transform, n of some sequence fi, this is going to satisfy the property 0 is less than that, which is less than n times m. What this turns out is, in the end, what we get is a multiplication of all of these elements. All of these are multiplied together with our other transform. So I think I can take away this matrix now. Our multiplication routine is a multiplication of two of these sequences. So when we multiply this together with another one, we have n times some f. We have another n times some g. But what that means is that if it's a pointwise multiplication, then the maximum that we can possibly get is going to be n times lowercase m squared. Again, if I write this out, if we have like 1, 2, 3, blah, 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 let's say that's our transform sequence, and we have another transform sequence, 4, 5, 6, blah, blah, blah. The multiplication of these, so this would be nf, this would be ng. When you multiply them to f times ng, you get 1 times 4, which is 4, 2 times 5, which is 10, and so on and so forth. So if the maximum here is nm, and the maximum here is nm, then the maximum for this element would be nm times nm, which is obviously nm squared. So we have nm squared in the transform space, but then we obviously do an inverse transform, and like I said, the inverse transform is it's basically has the same constraints of the original transform, except we do have a 1 divided by n factor. So we have our total nm squared over 1 divided by n, and this equals obviously n times our modulus squared. So through all this math, we found a bound for what our numbers can be. I talked about modulus here, but that's assuming that our modulus equals our base. If our modulus doesn't equal our base, then this would be n times... actually, no, ignore that. This can be n times m squared. M squared. Oops. Let me go back. So now we get into the representation of actual digits. Our input sequence is not actually going to be, so let me erase this. Let's write our little fact here. M, when we did that whole analysis, our input sequences might not actually be to M. In the strict number theoretic transform, they can be up to M. But if we choose a base B, like I said earlier, that is less than M, then we get markedly different results. Instead, our maximum representable integer in our input sequence is going to be B, and our output sequence is going to be, it's actually going to be M. So our bound then is going to be N times B squared. B squared. I think this is true. I actually haven't thought more deeply about whether this needs to remain as M or not. So we can go forward with this analysis a little bit more and actually discuss when we actually select our transform length and our base, we need to make sure we satisfy this constraint. So here's the problem. We need to select our transform length, which is, let's say, capital L. Let me erase this stuff up here. We need to select our transform length. Let's say X form length L, and we also need to select our numerical base, our integer base, capital B. For typical number theoretic transforms, L has a constraint. L must equal some power of 2 to lowercase l. We're going to call the lowercase l the log length, because that's what it is. This is the log length. Furthermore, our base B is probably going to be something that's close to a word length of our, I mean, if we can represent natively on our platform integers 2 to the power of 64, why not represent those as a power 2? So base B is also likewise going to be a power of 2. So 2, and we'll say this is lowercase b, and we'll either call this the base width or the log base. And so we get this relation then that if n times n squared, or likewise n times b squared, is our constraint, then we get the following sort of relation. N is going to be power 2, so we get 2 to the L. And then our maximum representable integer is going to be 2 to the b minus 1. 2 to the b minus 1 squared. Sorry, no, that's not right. Where is it? 2 to the b minus 1 squared. This isn't really, this actually should be b minus 1. Because this is the, I mean, if you choose b, it's right. We'll still get the inequality correct, but we can sharpen that inequality by doing b minus 1 here. Because if you're representing a number in base 10, for example, you have numbers 0, 1, ... to 9. So this is obviously b minus 1. Which comes here, this is b right here, so b minus 1 squared. Our constraint then is that our, how would I say this? That our word length, our maximum representable word on a computer, like for example our word length on a 64-bit computer is 2 to the 6, or it's 64 bits, and then our maximum representable integer is 2 to the 64 minus 1. We have this constraint that actually it's 2 to this. What is it? 2 to the. We have 64 bits, and that's 2 to the 65 5 minus 1. Let me think real quick. Yeah, if we have yeah, we would have 2 to the 65 minus 1. Yeah, I just need to make sure. So what we have then is that 2 to the whatever our word length is plus 1 minus 1 must be greater than or equal to whatever our maximum representable number is. So it must be greater than or equal to 2 to the L 2 to the b minus 1 squared. Expanding this out, or actually we can sharpen this a little bit. I mean, we have this little minus 1 here. This inequality will still be satisfied if we have 2 to the w plus 1 is greater than or equal to 2 to the L 2 to the b minus 1 squared. Whoops, this shouldn't be greater than or equal to, it should just be greater than. By the way, just as a little background, I am mostly doing this math on the fly, so I don't actually know if this is necessarily going to lead anywhere. I forgot to say that at the start, but it is what it is. So if we log both sides here, we can still, let's see, I want to take out this minus 1 here, but I don't know if that's a valid thing. It is. Okay, so we can be conservative here and say that our maximum word must be greater than something that's a little bit bigger over here. So to make this inequality simpler, we're actually going to rewrite it as 2 to the w plus 1 is greater than 2 to the L times 2 to the b squared, which is 2 to the 2b. When we log both sides, we get w plus 1 should be greater than L plus 2b. And therefore our word length w should be greater than L plus 2b minus 1. So as long as, so here's kind of one super important constraint, that our word length is bounded below by our log transform length and our base width minus 1. So let's write that up somewhere, that our big bound below is this sort of thing. I'm going to write it in some pretty color. Let's do bright red. So our lower bound is L plus 2b minus 1, which should be less than our word length. But now we need something else here to bound it above to make search possible. So let's erase this. And let's try to find a bound above. So what bounds our word length above? Let's see. Well, there's sort of obvious bounds that we have, like that our bound must be less than the actual realizable word length on our computer. Let's see.